All right. Hello, everybody. Okay. Well, since you've already watched the lecture video and tried Tool 23 here, you've probably gotten the impression that this is complicated, right? Um, Figuring out the properties of binary stars is tricky. It's a really slick trick, if you want to call it that. It's a really powerful technique for figuring out the properties of these two stars. Um, but there's a lot of steps, right? It's really pulling together a lot of things that we've learned over the last few weeks. And so it's a lot, right? So if this wasn't the easiest thing for you, then that's okay. That's kind of everybody, right? It takes some puzzling through. So let's go over this, right? Um, all right. If you've got these two stars, um, Alpha Centauri A, Alpha Centauri B, and we're trying to figure out what their masses are. What are the masses of Alpha Centauri A and B? All right. So you've got these steps right here, and if you wanted to do this, if you wanted to do this a little faster, then what would we do? Well, let's use a spreadsheet to do this for us. You could lay it out like this. I kind of set this up in advance so that it would look nice and be organized. But let's see here. I'll move the paper into view. All right. So the parallax angle from Alpha Centauri to Earth is what? 0.75481. How's that for significant digits? And the angular separation between the two stars is 17.6639 arc seconds. Okay. What does that mean, right? The angular separation is basically how far apart are those two stars? What is the angle between star A, Earth, and then star B? How far apart are they on the sky in terms of angle? And they're about 17 arc seconds apart. Okay. Then, how are we going to find the distance to Alpha Centauri? Same as always, right? The distance equals 1 divided by the parallax angle. All right, so Alpha Centauri is, and both of those stars, right? Because these two stars are right next to each other. These two stars are orbiting around each other. So they're both going to have the same parallax angle because they're both the same distance from us. And that distance, it turns out, is 1.33 parsecs. I could clean that up and reduce the number of significant digits, but leave it as is for the moment. How do you convert the angular separation into radians, right? Well, we need to. First off, we have to get the angle between the two stars into radians because it does make the math easier there in step 3. So, let's see. What do we know? We know that 1 radian equals 206,265 arc seconds. So then that angular separation in radians is going to be the 17 arc seconds divided by the number of arc seconds in 1 radian, which is the 206,000. Okay, and that's 8 times 10 to the negative 5, right? 8 times 10 to the negative 5. You should get a small angle. It should be a small angle, right? Because remember whenever you learned this in geometry class, right? 1 radian is a really big angle. 1 radian is a huge angle, which means that when you're measuring these tiny little angles between stars on the sky, you expect it to be a very small number of radians. So if you saw this on your calculator and you weren't sure if that made sense or not, it does. It should always be. The angular separation between stars should always be a small fraction of a radian. Okay, then step 3 is, if we know the angle between, I'm going to draw this here for a second, right? If you know the angle between these two stars, right? You got star A, you got star B. Here we are on Earth, so let's say there's your eyeball, looking at these two stars, right? The angle here is the angle S, and the distance from Earth to these stars is D, right? And what we want to figure out is this side of the triangle, Right? So we're doing a little bit of trigonometry here to say, all right, the semi-major axis, remember that semi-major axis is the average orbital distance, right? The average distance between these two stars that are orbiting each other. This semi-major axis, this side of the triangle, is just going to be the distance, right? The distance times the angle between them in radians, right? This equation only works. It's just A equals D times S when S is in units of radians. That's why we did the conversion in step 2. So now this makes it quite easy, because then, do this on my spreadsheet here, right? The semi-major axis A equals, there it goes, the distance in parsecs times the angular separation in radians, and that gives us the semi-major axis between these two stars. They orbit each other at a distance of 0.0001 parsecs apart, which is a tiny number because, you know, the stars are not very far apart. They're so close together that they're orbiting each other. So then the last step is, okay, but how many AU is that? Okay, well then, since there are 206,265 AU in a parsec, then we're going to take that, then take the number of parsecs times the number of AU in one parsec, and they orbit each other 23 AU apart. Okay. So now we know, put our answers on the next page like you did here, right? 1.33 parsecs, 8.5, what was that? 8.56 times 10 to the negative 5 radians. I'm going to turn that into scientific notation. 1.1 times 10 to the negative 4 parsecs, and 23.4 AU. All right. So, well, if we want to get the masses of these two stars, we know from Kepler's third law, we know that the total mass of these two stars orbiting around each other is the semi-major axis cubed divided by the period squared. How do we get the period? Well, that's where this light curve comes in handy, right? What is a light curve? A light curve is a graph of brightness versus time. And, right, what's happening here? What's happening is these two stars are orbiting around each other, right? And so if we look at these two stars, hopefully this is showing in the video, right? This is bluer and this is sort of yellowish, right? So this is the bluer star. Why is it blue? Because it's hotter, right? Well, this star is 8,000 Kelvin is how I've set it, right? This one is only 6,000 Kelvin. So it's cooler, and therefore they're going to be different luminosities, right? This is hotter, so it's going to be brighter, higher luminosity. This star is cooler, so it's going to be lower luminosity. So as these two stars orbit around each other, if they eclipse each other, right? If one star goes behind the other, then here we are. The cooler star, the dimmer star, is eclipsed behind the brighter star. And so if you're plotting the brightness versus time, then you get a little dip, right? Why is there this little dip in the light curve? Because we're only losing the light from the dimmer star. So we're not losing as much light, so it's just a small drop in brightness. And then the two stars go apart. Now we can see both stars. We're getting the total light from both stars. We're getting the total flux from both stars. And so the stars go back to 100% brightness. All right, and then they keep on orbiting around each other. And now I'm going to back that up for a second. Okay, there we go. Perfect alignment here. Now, the blue star went behind the yellow star, right? The brighter star, the higher luminosity star, went behind the dimmer star. And now we've got a big drop in flux. We've got a big drop in brightness because the brighter star is being eclipsed, we're losing all the flux from the brighter star. We're only able to see the light from the dimmer star, so the brightness has gone down considerably. All right, and then the eclipse ends, and now the two stars are side by side again, and as long as the two stars appear side by side from Earth, then their total brightness goes back up to 100%. We're getting the flux from both of them, and then one orbit has been completed, right? The stars started out, right? We started out over here with the little dip where the dim star is eclipsed behind the bright one, and now we're watching one full orbit from little dip to big dip to the next little dip, right? That's one orbit has been completed. One 360-degree orbit of the two stars around each other. So that's how we can figure out the period, is by watching these two stars, see how their total brightness, see how their total flux changes with time. And what you'll see is a big dip and then a little dip, and then a big dip and then a little dip, and then a big dip and then a little dip, right? Every time the bright star goes behind the faint one, you get a big dip, and every time the faint star goes behind the bright one, you get a little dip. And so how can we use this to figure out the period? Well, since we're watching these stars, right, the flux, the brightness of those stars is the big dip and then the little dip, and then the big dip and then the little dip. So one period, right, the period is the time for one orbit. The two stars orbit each other from one big dip, right, the bright star being eclipsed, to then the little dip, the faint star being eclipsed, and then the next big dip is the big star, the bright star being eclipsed again, right? So it's from big dip to little dip to big dip. Or just to shorten that, you could just go from big dip to big dip. That's one orbit. And so the time from this to this must be the time that it takes for the stars to orbit each other once. That's the period. So what's the period here? Well, let's add this to my my spreadsheet here. I'm going to say, all right, the period is the difference between these two. Get these back. Get these both in view here, right? The period is the time from big dip to little dip. So the first big dip happens on day 7,300. The second dip happens on day 36,500. Right, okay, got that right. All right, so then how much time does it take to go from day 7,300 to the day 36,500? Well, that's just going to be 36,500 minus 7,300. All right, then those two stars take 29,200 days to orbit each other. But what is that in years? We want that in years. So okay, I'm putting my numbers here. So, okay, in years, let me call these things line up nicely to try and make my life a little bit easier, right? All I need to do is convert, all I need to do is convert this period from days into years. So how many years is that? Well, it'll be that many days. Take that number of days, divide by 365 days per year, and that's 80 years. So these two stars take 80 years to orbit each other. So 29,200 days, or 80 years. Alrighty. Now, what's the total mass? Right? Now we know that the total mass, the mass of star A plus star B, we're going to be able to figure that out since we have the semi-major axis cubed and we've got the period squared. So, the total mass, and I'll just cover up the paper for the moment. Let's say total mass, right? That's going to be what? It equals the semi-major axis cubed divided by the period squared. All right, 2.002 solar masses. Remember how in Kepler's third law, the total mass is always in solar masses. the semi-major axis has to be in AU, and the period has to be in years. That's why we've been having to do all these unit conversions. Okay, so I'm just going to round that to, what's the total mass? The total mass is 2.00 solar masses. The mass of star A plus star B is twice the mass of the sun. Okie dokie. Then, how do we figure out? We know that the mass of A plus B. Okay, you know what? From here on out, I'm going to do this on paper, because from here on out, it's a little bit of algebra, and the algebra is easier to do on paper than it is in a spreadsheet. So, we know that the mass of star A plus star B is 2 solar masses. But we want to know what their masses are separately, individually. How do we figure that out? Well, we know from studying their velocities, right? From studying the velocities of these 2 stars, we know that star A must be 1.21 times the mass of star B. So we have 2 pieces of information. We know what their total mass is, and we know what the ratio of their masses are. And now we've got a classic system of equations, right? We can't solve for MA and MB separately with just this or just this, but if we use both of these pieces of information, then we can separate MA and MB and get both answers. All right. So if the total mass is the mass of A plus the mass of B, what is the mass of A? The mass of A is 1.21 times the mass of B plus another MB. What is 1.21 MBs plus another MB? Well, that's going to equal 2.21 MBs. Just a little bit of algebra here, right? We basically took this and plugged it into here to say, okay, total mass is 1.21 MB plus MB, which simplifies to 2.21 MB. So now the total mass, let's do this down here. All right. So now the total mass, 2.21 MBs, equals the total mass, which is 2 solar masses. So then the solution for MB, if we divide both sides of the equation by 2.21, the mass of star B is 2.00, since we had all these significant digits over here, divided by 2.21, which is, I don't have my calculator, but a spreadsheet is a calculator, so I'll just make my life easier here. What is 2 divided by 2.21? Okay, 0.905. Okay, so then the mass of star B must be 0.905 solar masses. So, just putting the placeholder here just to be careful, 0.905 solar masses. Okay, well now that we know the value of the mass of star B, we can put that back into here, and we know that the total mass, 2 solar masses, equals the mass of star A plus the mass of star B, but the mass of star B is 0.905, so then the mass of star A must be 2 minus 0.905. 2 minus 0.905, 1.095. All right, then the mass of A must be 1.095. Okay, now we've separated out, and we know mass A has a little bit less mass than the sun. Sorry, mass B. The mass of star B has a little bit less mass than the sun. Star A has a little bit more mass than the sun. And remember that the mass determines the luminosity. If star A has more mass, it's going to be higher luminosity. it's going to look brighter, which is why star A looks brighter in this picture than star B. It's a small change, but then it's a small change in mass. So now we know. And it's always good. It's always good to check and make sure that your numbers match basically your observations, right? This would imply that if star A has more mass than star B, star A should have more luminosity. And if it has more luminosity, then since these stars are the same distance from us, then star A has a higher luminosity, so it should give us more flux. It should look brighter in the sky, and it does. Great. Then what we're seeing in our telescope matches what the math is telling us, which is always a good indication that we did the math correctly. All right. One more time for good measure. Now that we've set up our spreadsheet, this will make quick work of this, all right? What if we're looking at the two stars in the Capella system? All right? Capella A and Capella B. If they have a parallax, I'm going to move this up and this down this time. All right. So Capella A and B have a parallax of 0.07602 arc seconds. So they're 13 parsecs away, and the two stars are 0.05662 arc seconds apart on the sky. So these should be your answers here. 13 parsecs, 2.7 times 10 to the negative 7 radians. Like I said, it's always going to be a small number, which means that those two stars are 3.6 times 10 to the negative 6 parsecs apart, which is close, right? What is that in AU? That's 0.7 AU. Remember, the Earth is 1 AU from the Sun, so these two stars are orbiting each other closer to each other than Earth is to the Sun, which is pretty intense, right? You'd think that if those two stars are orbiting each other so close, they must be orbiting each other really fast. Well, let's see what the period tells us. If, what did we say about AU? 0.74 AU. Okay. So these are, you can fill in the rest of those. How about the period? Well, again, the period is the time from big dip to big dip, which is the time from day 26 to day 130. So instead of these numbers, I'm going to say, all right, day 130 minus day 26 is 104 days, which is 0.28 years. 0.28 years. And then that means that the total mass, since I've got the semi-major axis and I've got the period, then they must have a total mass of 5.05 solar masses. All right, but what about their separate masses? What about the mass of A and B separately? We need this, right? We now know that the mass of A plus the mass of B equals 5.05 solar masses. And we also know that the mass of star A equals 1.04 times the mass of B. So let's take this MA, plug it in here, and we'll say, all right, 1.04 times MB plus another MB equals 5.05. What's 1.04 MBs plus another MB? 2.04 MBs total is going to equal our 5.05 solar masses. The mass of star B is 5.05 divided by 2.04, which is 5.05 divided by 2.04 2.475. We'll do that. So so the mass of star B is 2.405. That's not what I just said. 2.475. Okay. So MB is 2.475 solar masses, and A, right? We're going to go back here. The mass of A plus the mass of B equals 5.05. So then the mass of A plus the mass of B, which we now know is 2.475, equals 5.05. I'm running out of space here. Okay. Subtract this from both sides, and MA equals the total mass minus the mass of star B, which is then 5.05 minus 2.475, 2.575. 2.575. There you go, right? Star A has a little bit more mass than star B, which is exactly what this says right here, that the mass of star A is 1.04 times mass of B, so star A is just a little more than the mass of star B. There we go. Really close, right? Their masses are really close. And since their masses are really, really close to each other, since their masses are so similar, their luminosities are going to be similar. And therefore their brightness on the sky is going to be similar, which is why they look pretty much the same brightness here on Earth. All right. It's a long walk to get here, but it's a fantastic way of figuring out what the masses of these two stars are individually. Right? You can't just look at a star. You can't just look at any old star and say, look at that star. I know what its mass is. You don't, right? You can look at a star and measure the parallax to get the distance. You can measure the flux to get the luminosity. But what's the mass? Right? By using the gravitational pull of these two stars orbiting around each other, we can figure out what their masses are. And once you know the mass, you know everything. Because the mass of a star is its destiny, right? And so this is why we put up all this effort, right? We put up all this effort because we want to know what the masses of these stars are, because if you know the mass, you know pretty much everything. So it's a big payoff. It's a lot of work, but it's a big payoff. Okay. Hopefully that makes some sense. And, practice with this a little bit more, check your work a little more, and like I said, this is the hardest thing we're going to do this semester. So if this has you with having a real headache, the silver lining is this is the hardest thing we're going to do. And everything for the rest of the semester is easier from here on out. So I hope that makes your day a little brighter. All right. Have a good one, everybody.